Okay, we might as well get going with this. Welcome back to the channel. Thanks for hanging out with me again this evening on the Twitch. If you like what we're doing, definitely like and subscribe. Hit that bell notification to be informed when we drop new videos on YouTube. It means a lot. I'm enjoying doing these videos, and I definitely want to do more. And any interest is definitely helpful. Don't be afraid to leave comments on the videos, ask questions, just be respectful and civil about it. If you're on Twitch, don't be afraid to ask anything in the chat. I will do my best to answer as I can. I do get lost into my work and lost in my head, and sometimes I stop paying attention to other things. So if you do ask questions, I'm sorry if I miss it. So the last video, we received parts. DigiKey and the Mauser order came in. So we had a whole swath of parts that needed to be checked in and gone through the process of code. There we go. Incoming inspection. So we pretty much went through the incoming inspection on those parts. I went ahead and did the rest of the Mauser order because there were so many parts. I'm not going to waste your time. It took around an hour to go through, follow this process, properly label everything, affix the MSL labels to the barrier bags so everything gets tracked and followed properly. Everything's all set up. Everything's done. We're happy with that. So another thing we'll run into is some parts you don't necessarily get a lot number with. Now, if lot tracking is extremely important to you, or you want to make it extremely important, or if your customers 100% demand it, or you just want to just make it universally required throughout your entire process, you might want a work instruction on to generate a lot number for when you get products that don't have a lot number attached with them. That's sometimes just the way it happens. Sometimes vendors don't give you a lot number for the product. The majority of the time you will get a date code. There are times that you don't even get a date code. So for if when traceability becomes super important, a lot of times you can at least just generate a lot number. So maybe down the road we will generate a work instruction for how to generate lot numbers for products that don't have one, just for traceability. But you know, that's why we're also keeping the paperwork that comes with everything, and we're logging the date of receipt on the product. On the product label, we could even on the product label expand it to include the purchase order number that they received on. If you're so inclined, then you could tie everything together even better to the purchase order. But generally, the date of reception, as long as you have like this, things will kind of tie together. You have your date because then you can search and find your POs and everything, and tie and find your invoices that way. So there's always ways to backtrack and figure everything out. So all that's done. We're just waiting on PCBs and the stencils to come in. And that's probably still about a week out. I just checked the manufacturing progress on JLC PCB, and they're still in the manufacturing process. Let me double check real quick. Just pop over here to my other screen. What's great is they do have a way to, my histories, yeah, production progress. So they're roughly 68% done. So, you know, there's like 22 steps. They're at step 16. Basically, they're applying the silk screen to the boards. So they're about 68% done. So I imagine they may ship by Monday. And then got to give them time to get it, from China across the pond. So just wait on that. So definitely sometimes next week they should be in. And if we're lucky, we could start building. Actually build our first pilot board. So we know those to come in, so we might as well get caught up with some of the paperwork. And that is going to be basically our test plan. Kind of get going on this. Wow, I am great. So one of the things I wanted to do is also pull up the schematics so I can pull in test points, so I know what in the world we're measuring, and I could actually call out test points in the plan and in the test plan log. So the first thing was the visual inspection. So in resistance mode, we want to check between TP. So we'll go to the schematic. So we want to kind of check the two power supplies, TP1 and TP3. TP1, 3.3 volt, and TP3, ground, and verify that the 5,000 ohms. Now, you're not going to have an open there, because for one thing, you do have pathways on the 3.3 volt to ground through things like this diode and this resistor, so you're going to have some resistance. So also through capacitors. So what you'll see is over here, these filter / bulk caps over here. They'll start charging up when you apply your multimeter, so you see the resistance start kind of low and then slowly start climbing. So you definitely want to make sure your resistance is roughly around 5K or more. It should eventually climb into a higher range, but because we've got these LEDs, we have a resistor and a diode, there is a path between volt to ground, and you will have a resistance path. So it will never be infinite open resistance. As long as you're reading definitely greater than in the tens or even hundreds of ohms, you don't have a direct short. That's what we're really looking for, is a direct short. Because if we're in the 100 ohms or less on the 3.3 to ground, that means we have a solder bridge somewhere, or we have a failed part, or a component could be backwards, or we have a capacitor or a resistor where there should be a capacitor or something. Then that's always a possibility. Somehow maybe a 100 ohm, like a 330 ohm resistor or something got placed here on one of these cap spots instead of a capacitor, or even 100 ohm for parts of the other parts of the circuit or whatever. So if you're below a certain resistance rating, you've got a problem, and you need to figure it out before you even consider applying power. That's what this test is for. Verify that the resistance is greater than 5,000. We'll start that, but typically what I've seen, it's usually going to be between 3 to 5K is where your range is going to start. If the is below and for issues so solder bridges are going to be your more common faults, your more common failure. And yes, you want to spell all those out. It's part of the process. Leave as little to chance. That way an operator or the technician who's doing this test may not be the engineer that designed it. Maybe just an engineering tech. Could be an intern. Could be a co-op or anything. You want to make sure that all this is spelled out. Because if you think back to the RACI chart, basically the responsibility and accountable chart, you want to make sure that they know basically what their responsibilities are and what they should be doing if a failure has been determined. I think we saw if if a problem is not so yes, even though I'm a team of one, I'm writing these SOPs in the way that if I do grow a business and it becomes more than just me, I don't have to go back and revisit everything. Right now, it's automatically assumed I'm everything, so I definitely automatically assume that. But for next step, so again, spell it out. Spell out the responsibilities, what the person is supposed to do if these problems are encountered, because there's no reason to continue this test. There's no reason to continue this process. If you've got a short in your 3.3 volt line and you can't immediately resolve it, you don't want to apply power to the board. You're going to fry something, and you just defeated the whole purpose. Because if this becomes a bigger issue, then why bother with it? If it's just an SMT issue, if a part was put on backwards or whatever, and it's solvable, then you would basically come back to this process and start over. So what we're going to do is, now we've got that as one of its own. Let's go here. So we might want to kind of break this up. Let's one. Let's kind of do this. Let's kind of expand on this. See, then we can do 2. So this might be a little bit easier to follow and do it that way. Is the greater than or equal ohms? The result notes. So if it was a fail, you put a fail condition here, and put the notes like it was fail. It was elevated up to whoever to take care of it, or you would put like what the problem was. Like if you inspected the board and it turns out like a part's backward or solder bridge, you would put the resolution there. You could even kind of put a note after it failed. We did this, then it passed again, then it passed. Or you could put this aside and start a whole new test plan log for this board, for that same board, and just start over. We will have to define all that as we go. So then here, so kind of breaking it down here. S3. So what we're going to do is we're going to copy this. Yes. TP1. So that is TP2 and TP3. Same thing. So what we can do here is also clearly identify it should be a positive. It's going to be positive. Not that it really matters. So that's the same thing. So it is TP2 and TP3. It's 3. All right. So these are initial testing. Again, these weren't kind of, AI didn't kind of write them. We might want to actually, we'll probably update the traceability metric, make sure, come back to that later. I forgot. I have to open it up in Excel or LibreOffice. So we might kind of write this first, kind of referencing I'll go back and kind of reference what AI put down. And that way it'll just be a little bit easier. Because this is the way I'm used to writing these kind of things. And not, I usually don't use AI. But I do want to make sure that everything's covered. That's why I use Copilot to help generate that. Because I want to cover things I might miss through this series, other, requirements. I want to make sure everything's covered. So let's see here. That's the initial resistance. Let's look at the schematics. Should there be any other resistance that we want to verify? And yes, there will be. So the ESP32, no test points here. RS45, test points. Yes. So we will want to make sure that we're not shorting out anything out here. I mean, even though if you accidentally short out the A and B, it's not going to damage the transceiver at all. It just won't function. So it's best to avoid shorting it out. And we will check that resistance too, to make sure there's no hidden solder bridge underneath this chip or something that was missed during the initial inspection. Again, this is the initial first test plan for the first article board. It's going to be a little bit more involved, a little bit crazier, so we will actually include these test points too. And I'm not sure exactly what the resistances will be, so we'll just kind of throw in a value and see what we get in actuality, but it should definitely be greater than 0 ohms, maybe in the couple hundreds. Should definitely be greater than 1K, if I'm not mistaken, because, going through the IC or the ESP32 on this side. But we will want to make sure there's no shorts anywhere. And again, this is all before we're applying power to the board. We don't want to cause any problems. So that's 4. All right. Again, check between test point 4 and 7. I'm confusing myself. 4 and 7, which is ground. Because if any of those signals are accidentally grounded, you're definitely not going to get communication through that. Because this verifies more than just that you designed the board. It also verifies that it was built properly. Because if you came in, and I'm just going to be blunt about it, if you came and build a pilot board right without problems, without having solder bridges and stuff, I mean, I can understand if it's your first board, the first time you've ever done this, yeah, you're going to probably run into problems. But after about your 5th, 6th iteration, your 5th or 6th design, if you came and assemble a board properly and have it reflow properly, you've got other problems other than just design problems. And when that magnifies into full-scale production, that's typically referred to, a process out of control. So if you have a team like an SMT, like an assembly team doing the SMT line, you have a technician team doing, technical team doing the through hole hand assembly, whatever. And if they can't even build a board right after building multiple boards, then your processes are out of control and you've got a bigger problem than just something else. And that requires other things. And then you're looking at like Six Sigma type intervention or other problem solving techniques like, just do it, Kanban, pull in, experts from the outside to help you solve your issues because you got problems greater than this. But for a prototype board, we want to make sure everything is built properly before we even power it up, because we don't want anything just to fry. We don't want to damage any of the parts we just spent money for. And our first board, we want to make sure it's fine. So it's TP4, which is 45RX. So we're going to assume it's going to be greater than 1K. Because at signal levels, 1K, you're not really pushing a lot of current anyway. And most of these devices will kind of shut themselves down or not even do anything if they detect a direct short. But you just kind of want to check it, because if it doesn't work, if you've got a short already, and you can identify it and fix it before we even apply power to the board, that's even better. Because why get into trying to develop firmware and do testing if it's not going to work, and then you're going to have troubleshooting anyway, so you might as well just kind of check it now. Now, if it doesn't work and it passes this test, then that's when you got to do deeper troubleshooting. It could just be firmware. So let's see here. Again, elevate to direct supervisor for next steps. So yes, these test plans are going to get wordy. But again, leave nothing to chance. That's the great thing about these processes. The great thing about ISO. You leave nothing to chance. No arguments. So let's see here. It goes here. That's test 4. And this is, again, this isn't the production test, which would be a lot simpler than this. 4 and 7. Seven greater than equal to 1K. Okay. Make sure we changed that. All right. So we're going to do test point 5, which is the 45 direction pin. Nope. All right. Yeah, I can't type worth a darn. Artifact there. And then 6 and 7. Thanks. And it's going to be RS45. Make sure that we spell it. Test 6. So we'll go here. So that verifies no direct shorts between ground. And the ironic thing about doing this is writing this is going to take forever, but actually running through the test, it's just really quick. You just click, your multimeter, and you're just tacking onto these test points, just one after the other, and it's going to go by really fast. That's the sad part about documentation, and the design and documentation are the longest parts of any of these processes. But in actual practice, when you actually start doing this, it like you click right through it and you're done. It may take you 20, 30 minutes to run through this entire test, depending on how in-depth it's going to be written. Maybe a couple hours, but maybe because we've got a thermal chamber and we've got to let it sit for a couple hours. Who knows? But we'll see. But most of it's just sitting and waiting. But actually performing most of these tests, you're going to click right through it. That's the sad part about all this. Now, so we're also going to go between, make sure there's no shorts here, 4 and 5. TP 4 and 5. 4 is RX and 5's DIR. R. Okay. So 4 and 5. And again, these will serve, this stuff serves as the artifacts to prove that, yes, I tested the product. It met all the specs that we called for, that we say it's going to do, and we tested and we verified it. That's all this is about. It's just proving that you're doing what you say you're doing. 8. So then 4 and 6. 6, which is TX. Six. So this. Oh, okay. I could just do that. All right. And then we'll want to do between 5 and 6. Eight, 9, 5, DIR. All right. So is the resistance between TP 5 and 6 equal, okay, greater than or equal 1K. All right, perfect. Now, let us check. Yeah, we don't, since there's not a test point, but we can still kind of check the resistance here. Terminals 1 and 2 of CN2. That's the A and B. We can check and make sure we can actually run 2 separate tests. Here's what we can do. We can run one test, open, J1 off, not enabled, not connected, and we should get greater than 1K. But with J1 enabled, we should get 120 ohms there. Roughly, considering any parallel resistance, but you shouldn't really get much. 120 ohms is going to be the shortest path. So that'll check the terminating. There should be pretty much isolation here between the A and B channels internal to this chip. So realistically, when you measure between these two, the resistance between these 2 points, this should be an open. Should be completely open circuit even with this TVS in here. Because its path is to ground anyway. And you should only get a resistance when you enable this jumper. So let's go and test 9. Oop, no, test 10. Jeez Louise. copy so the wording's the same. Using an alternate check between CN2 terminal 1 and terminal 2. CN2 and verify and terminal and verify. The wording, I don't know. Maybe we can fix that. Too many ands there. I don't like it, but in some ways I don't. I'm not here to be a spelling or grammar professional. It's just to get the job done, if it makes sense. You know, maybe you want to pay attention to your grammar. If you're doing this for a customer, try to come up with better wording. But at the end of the day, the whole point is just to do this. And, you know, grammar police, seriously, you really want to split hairs over that. So test 10. I could have dragged that down. Let's see here. Actually, what I can do is... Yeah, so I'll overwrite that between... Let me say that CN2. CN2. Short-term memory. 2. Okay. So now this, I'm gonna kind of tilde roughly equal to 120 ohms. So it might be roughly equal, depending. Oh, thank you for advertising on my chat. Yeah. Woo, hooray. So we're going to run here, since we know it's going to be test 11. Test 11. Use an alternative in resistance mode. Place a jumper on. I better spell it out in the first one to make sure there's no jumper there, but let's finish writing this one. J1. J1. And then is around 120 ohms. Below is too low. We're going to go 50, not 50 hertz. We'll kind of throw a range, because if it's, with that resistor, if you're below 120 ohms, for a single board by itself, you could have problems, because the way buses like this, communication buses, especially those based on RS-45 or CAN or other buses like that, which are technically built off of the RS-45 system, the transceivers are almost identical in operation and everything, like Profibus and stuff. What happens is you only terminate the first and the last device in that bus. But if you accidentally terminate every device in that bus, let's say you have like 10 devices, you're basically going to short out the A and B lines, your communication lines, and they won't work because the rules of parallel resistance apply. So even with your first and last device terminated, your effective resistance is only 60 ohms because it's halved, and anything lower than that. So if you're already getting weird measurements here, especially lower measurements, and you don't even have anything connected, you've got a problem somewhere. Resistance mode. I don't know why. Ensure that J1 installed. Then we can just change that to install. And we can leave the jumper on, because technically for a single device, leaving that terminated is not going to hurt anything. So if you're talking between this and, let's say, another microcontroller or a PC or a Raspberry Pi further up the chain, leaving the terminating resistor on here is not going to be a problem. But it's up to you, because then you can change it for shipping. That way, during the packing and shipping process, the technician removes the jumper and places it on there. Or removes the jumper and just kind of sets it in a non-enabled state. So that's a whole other thing. And basically what you want to do is, down the road, before you actually start shipping these units, create like an out-of-box checklist. I'm just covering that right now, because you'll take all these steps through here. Well, not really, because you'll be in a production test. Basically, you want to create this checklist or this process for that product. So anytime a customer orders this product, they pull it out of the box and it's basically set up the same every time. For one thing, that'll make sure any instructions or documentation you ship with the unit makes sense. Because if it tells you the jumper's not installed, it's just, sitting there, and it's installed, it'll get kind of confusing. They might think that they got a used product instead of a new product. And it just becomes a customer service. It could become a customer service nightmare. Some customers don't pay attention, but some do. So you'd want to kind of have like an out-of-box checklist. That way every product matches the same every time one is bought and unpackaged by the customer. You could call an OEM, configuration, but out-of-box is the term that's typically used. So for now, it can just stay in. It doesn't matter. It's not going to hurt anything, even down long-term testing. So that's test 11. Make sure around or equal to 120 ohms. That's your terminating resistor. So here, so that checks that resistance. That should be done. Limit switches. Now there are test points here. Even more things we can check. Even more things to document. And again, it becomes a load of fun, because again, you could have shorts here between your output off of your opto isolator. And if you're shorted out here, your microcontroller is never going to get the signal. And then we'll want to check a few other things here without this jumper, all this other stuff. So let's start with the most logical things, which are the test points, and then we'll kind of come over here. So, and we're still doing the resistance test. We're still on this initial resistance measurements. Again, wordy, but at the end of the day, if you want to change this for your company, your processes to be less wordy, that's up to you. How you do things is up to you. You don't have to follow what I do. Okay. Make sure I don't confuse myself. Test 12, which I don't have over here yet. All right. And we want to go test point 10 to 13. TP 10 to 13. So what we're going to do is kind of copy, because now we're back to this type of stuff. So No jumpers there. Make sure 10 and 13. And we'll go through and we'll kind of like double check, make sure I don't have, we have extra spaces and stuff. So test point 10 is limit 1 and then ground. Limit 1 and ground. Okay, 1K is fine. So this I'm just gonna drag to my other monitor so I don't, have to keep flipping to this. I already have to flip between all this other stuff. Because I'm just basically this is just gonna be a log. And we'll just kind of do this as we need to add more cells to it. We'll just copy and drag that down before we get down to it. That way I can kind of save on stuff, save on effort. Hopefully be a little less boring. And I'll set up so I can still look at the stream chat if anybody wants to participate. So 12, okay. And that way I don't have to keep referencing back. That's 12. Ten and 10. 10 and 13. My goodness, I'm a real winner. 13. All right. Now. And yes, before anybody asks, I have seen this before with working with people. The human factor always applies. If you don't spell things like this out, people will jump steps. And even though logically you would think that, oh, if I need to stop, if I run in this condition, I need to elevate. If you don't spell it out, people will take advantage of that. And they will do whatever. That's another reason. It's kind of a shame that you have to do this. But I have seen this time and time again in real application, real manufacturing environments. If technicians will, people are people. If they find a way they can change their work, shortcuts, if they can cut corners and not get in trouble for it, they will. It's unfortunately the name of the game. And that's just something we have to remember. We're dealing with people. That's why everything's so wordy here. So, yes, copy, paste, make sure I change that. TP10, so we know where that's 11. Limit 2. Oops. 11, limit 2. And again, we're going to put it over here. Test 13. Again, you're not going to do this stuff in a production test. This is only for your first article. Your real hardcore checks to make sure that your design is ready for that stage. Okay, test point. And I bet you it's going to be 12 and limit 3. All right. All right. Now, so what we can do now, and what I would suggest is also make sure that you don't have any shorts between these guys, because you could be sending a false signal to the ESP32. Because if this guy triggers and it also triggers this guy at the same time, that's a false signal. You're gonna have a failure. So 10 and 11. We'll see. That's 15. TP 10 and 11. So 10 is limit 1. And that would be limit 2. All right, and again. All right. 15. Now, the other thing too, this could be 11. Oh no, we're going to keep it on limit 1 and go to limit 13. What's going to be limit 3? Idealistically, in a larger environment with more people, you'd have somebody read this and make sure it all makes sense. Basically, a sanity check. They check to make sure that it's followable, that it can be done. You just basically have checkers, people making sure everything makes sense. But unfortunately, again, a team of 1, we're going to do the best we can and cross our fingers. Hope for the best. All right. Save that. So that is limit 1. 1 and limit 3. Okay. Check between. Now we're going to check between 12, limit 2 and 13. And that should verify that there are no shorts anywhere in there. All right. All right. So we pretty much checked all of these guys. There are no short, for checks for shorts over there. Now what we're going to do is all these guys are tied into a bus. We want to just verify the functionality of J2. I mean, we could go through and check all these guys for shorts, which technically we probably should. And also make sure they're not connected to ground at all. Again, because if these guys are connected to ground, your inputs will not be received. So that is something we probably should do. So CN3. So we're going to kind of... look up our CN, our first CN. Here we go. We're going to kind of copy that because the wording is going to be very similar. Okay, so it's going to be 18. Sure that J2 does not have a jumper installed between CN3 CN3 between 1 and we're going to make sure there's no ground ties. Well, actually, that almost doesn't matter. Well, it actually kind of does. We want to make it sure between 1 and 4. 1 and 4. This is greater than 5K. Because again, that's your ground isolation right there. Multimeter resistance measure J2 does not have a jumper installed in check between CN3 terminal 1 and terminal 4. Resistance greater than 5K. All right, that makes sense. Because that's an input. CN3, terminal 1 and terminal 4. 4, and we're going to put that to 5K. Drag that guy down. All right. $19. Make sure that matches to the spreadsheet. Yes, it does. It does not have a jumper installed. Terminal 1. Go to 2. Terminal 4. Yeah, because if you've got no jumper there and you do have a connection between these guys and ground, because you're still got your limit connections here. Yeah, you definitely don't want to. Let's see, you still actually will have resistance, so we might have to actually change the wording to a greater than 1K, because you're going to have this resistor, that's right, because you're going through a diode, and that's your common. So yeah, we're going to change that wording a little bit to make more sense. So it's going to be greater than 1K. My mistake. I wasn't paying attention. I was looking at the ground connection. But since that's common, that's whatever you're setting your common to. And you could set it to internal ground through that jumper. So at that point, it doesn't matter. All right. And then... Okay, plus 20. Terminal 3. Oh, let's fix this. 1. Because again, you're going through that resistor and the diode, the LED, and the optic coupler. 3 and terminal 4. Okay. Well, 3 and terminal 4. Okay. So logically, the logic train would apply that you should still be greater than 1.2K. You're not directly shorting any of these guys out. So putting the jumper here should not make any difference, because if you're at 1.2K between each of these and that terminal, you're not shorting anything out. But if you're jumping between 1 and 2, that's what we need to check. That's where the greater than 5K should be in. So we don't need to worry about the jumper, because it's irrelevant at this point. Mode. Check between 1 and 2. And then 5K. Because we don't want to short between that input and output, because we don't want to trigger both of them falsely. We don't want to false trigger. That's what we're trying to avoid there. So come back over here. One and 2 greater than 5K or equal to. All right, 21, and then we're gonna go here. Test 22. Terminal 1 and 3. 3. Then this should capture the last one. You see in terminal 1 and 3, 2 and 3. And that should capture all of those variables. 2 and 3. Sure that's saved. Okay. Back to our schematic. So that covers this guy. Now we have the control inputs. Basically, the same things are going to get written over again. So I think what I'll do is, because this is going to get boring, because I'm basically going to be duplicating all this for these guys. I'll kind of get that caught up off camera, because we're already running in towards an hour of this video. And I don't want to run too much time on these tasks. What I'll try to do is, before the next video, at least get this stuff caught up on the test plan and into the log. That way, we can jump in to some of the next stuff, like writing the test for the USB UART, because we definitely want to make sure there's no shorts in here, and that'll be, a bunch of different little test plan, and then the stepper. So we'll check all that. We'll get all that caught up. Because I think, let's see here. I don't think I broke out test points for all of these little guys. I probably should have. The stepper fault, I probably should have. But I didn't. And I'm not going to worry about that too much, because there are places we can measure, like off these resistors and stuff, if we really need to. I should have thrown in test points. That was my fault for not throwing in test points for those. And I know I didn't, because they're not over here either. But yeah, I'll get this, and then the next one we'll catch this one, and then hopefully start writing the additional tests, like first time power up, basically the bench test, the smoke test, make sure the Magic Genie actually stays in the parts, that the Magic Blue Genie doesn't escape. We'll write the test plan for that. Basically, the unloaded test, the unloaded power, current limiting, see what it does. Make sure we're not triggering the current limiting on the power supply. And then checking the 3.3 and the 5 volt supplies, kind of making sure that they put out the right voltage, kind of look at the unloaded ripple on them with a scope. See what we kind of get out of that. And then kind of start writing the other tests, like we'll have to figure out what kind of tests we're going to want to do to load the device up, because we're going to want to make the actual stepper driver actually work. We're going to want to make, we're going to definitely hook a motor up to it. We're going to want to devise tests for how to run it, for running it and things like that. Check the temperature of this guy, because we're also going to want to reference the temperature chip. We're going to want to make sure that maybe put a thermocouple kind of on the board. We'll kind of figure all that out, because let's go in here real quick, kind of give you ideas of things that we're going to go do. Since the thermal sensor, the temperature sensor is right here. We will probably see about fixing a thermocouple, kind of like right here, doing some temperature readings directly on the board. and kind of trying to compare them to a reading. We can pull off the thermocouple. We'll have to rate, obviously, firmware for that. We'll rate firmware. I have firmware for the fan for the ESP32 already. It's basically a drop-in component module. We'll just kind of build it, expand on it for this purpose, because we'll have it temperature driven off of this guy, kind of figure out some ranges. But we'll do some very basic test code. So we'll probably be plugging a bunch of different test code on the ESP32. Most of it, that'll be just testing various functions, basically getting like inputs, lighting the status light, things like that. And then we'll start piecing things together into a more functional bit of firmware. So that'll take some time. But for now, at that point, we'll just be doing a bunch of testing. We'll just be testing individual blocks like the inputs. Like I said, the fan, we'll make sure we can read this guy, a basic RS-45 terminal, using a USB to RS-45. I'll show you real quick. Bring it up. What I'm going to be using. Let's see if I can pull it up here. Right here. So just drag this into the screen. So basically I've got one of these. It's a USB to RS-45 converter adapter. So it can work Windows, Linux, most operating systems. It basically just becomes a serial port. So you can use something like PuTTY. And that's what we'll be using. I'll be using PuTTY with this. And we'll just do a basic terminal. We'll have the first terminal. We'll have one for the generic UART debug. That's USB UART. Here we go. With the UART debug, we'll have a basic terminal, and then we'll expand one that will incorporate RS-485. Because if I'm not mistaken, the ESP32 has functionality. You can tell it you're using an RS-45 and then where the direction pin is, and it can control that automatically. It'll basically be in receive mode and then go into transmit mode and stuff like that. So, but we'll do that, and we'll be using RTOS and separating these tasks out. Have separate tasks with ISRs and stuff. They'll be able to handle themselves. So we'll definitely be coding a little bit of firmware. And I'm going to keep saying this. I am not a programmer. I'm teaching myself as I go because I really love working with this stuff. So I'm teaching myself firmware development just so I can learn so I can actually build things that actually do stuff with these chips. The world's no longer analog like it was when I first got into this. So I pretty much have to either learn how to write firmware or pay somebody else to write it for me. And honestly, I like learning, so I prefer to learn it on my own. So my code is not going to be elegant. It's not going to be beautiful. It's going to be rife with mistakes, but it'll work. And that's the key. And I'll be Googling a lot of stuff to writing my code. But like I said, I have some drop-in modules, like for the fan, for the PWM TAC fan that I wrote for another project I'm working with. We'll do one for the temperature sensor. We'll definitely have one for the stepper drive and everything else. But we will get there. For now, though, I think I'm just going to call it here because I don't want to go too long over an hour in these videos. And I'll get the other test plan written for the control inputs because, again, it's going to be a copy and paste of the limit, so it's just all the wording changed to match the test points and the connector and stuff. So I'm not going to sit here and hold you for 20, 30 minutes while we do that. It's just not going to be fun. So I thank you for checking us out, for hanging out with me. Really appreciate it. And let's see, it's Friday, so I'll be streaming and recording my next video tomorrow afternoon at 2. Feel free to join. Hopefully by then I should have that test plan that's updated and ready to go for when we start. Thank you. Have a great rest of your evening, and catch you tomorrow.